Welcome to springlib.
Okay, in this problem, we're interested in looking for the minimum work function for a metal in order to eject photoelectrons using visible light. So we're given a range of wavelengths for visible light, ranging from 380 nanometers to a maximum of 750 nanometers. And we need to find the minimum possible work function to eject a photoelectron. So this is the photoelectric effect. The main equation that we need to use is this one, K equals HF minus phi. And this is essentially conservation of energy. The kinetic energy of an emitted photoelectron, let's draw a little picture here. If we have incoming energy due to light, and that energy is proportional to the frequency of the light, then we can eject photoelectrons with a kinetic energy K. And that K value is going to simply be the amount of energy given to it by the light minus this threshold work function needed to eject the photoelectron in the first place. So that's this equation here. Now, we're not actually given any frequencies in this problem, so we need to actually determine a wavelength of this light given its frequency. So we can use this second relationship, C equals lambda F. And we're going to need two constants in this problem. We're going to need the speed of light, which is approximately 3 times 10 to the 8 meters per second. And we're going to need Planck's constant, which is in this particular form, 4.136 times 10 to the negative 15 electron volts per second. The reason why we're going to use electron volts is because since we're considering single electrons being ejected from a metal, the amount of energy in joules is going to be so small that it would actually be better to use electron volts. So let's get to solving this problem. Okay. So starting with our formula for the photoelectric effect, K equals HF minus phi, the work function. Now, if we're at the very threshold, in other words, the frequency is equal to its threshold frequency. So if we're at the very minimum possible energy of light to emit a photoelectron, we can say that the kinetic energy of that photoelectron will be zero, because there'll be nothing left after ejecting the electron. There'll be nothing left to give to its kinetic energy. So this is the limiting case we're interested in, where K is 0, F is at this threshold, and we have phi. So rearranging, we can solve for what this phi would be. And it's simply the product of H and this frequency. Now, using our C equals F lambda, we can reformulate this as HC over lambda at a threshold value. And you can see that because H and C are constants, the only thing we can actually vary to minimize the work function, which is our objective, the only thing we can vary is lambda. We have a range of lambdas in our problem. And what the lambda that we need to choose to minimize phi is the maximum lambda we have available because it's in the denominator. So using our largest value of lambda, 750 nanometers, we can determine the corresponding work function, which will be the smallest possible one in our range of possibilities. Can do this calculation, taking the Planck constant, 4.136 e to the negative 15 electron volt seconds, the units of H, times the speed of light, 3 e to the 10 to the 8 meters per second. Divide that all by our maximum lambda we have available, which is right at the edge of the visible spectrum, 750 e to the negative 9, because we're nanometers. And doing this computation, will give us a value of 1.65 electron volts. So for the visible spectrum, in the best scenario, the work function of our metal is going to be 1.65 electron volts. So in other words, so when we shine light onto our metal, 1.65 electron volts worth of energy is always going to just simply be lost to the metal. The rest will go to the electron, to the photoelectron, and giving it some kinetic energy. But this is the minimum amount of energy that's going to be lost. As we decrease the wavelength of our light, rather, this will increase correspondingly. So in other words, shining light on a metal to produce photoelectrons will be less efficient as we increase the frequency of that light or decrease the wavelength of it. So this is the best case for phi. This is what we're asked to solve for. This is the minimum work function for visible light. Thank you.